Hello students, we are here with another lecture on engineering thermodynamics, specifically meant for chemical engineering. Today we will discuss change of state of a system. We have previously discussed what a system means, so this is a carry forward from the last lecture. So let us begin. In this lecture we will cover what is a thermodynamic process, we will cover what are some different types of process, and we will also check how can a function be a state function? I mean, how we can determine whether a function is a state function or not. So to begin with, what is a thermodynamic process? A thermodynamic process is something that we call the change of state of a system from one state to another state. That is, the pressure or the volume or the temperature or all of them or a combination of them changes from one value to the another. And how does this happen? This happens when energy enters or leaves the system in the form of heat or in the form of work. And this can take place in several ways. What are they? The first is a cyclic process. In a cyclic process, the system starts and returns to the same thermodynamic state. The point where it began, the point where the parameters where the process began, the process then returns back to the same value of the parameters. If we check the diagram, it will be a little bit of clear. So say the system starts at point 1, it takes a path and goes to point 2, that is state 1 and state 2. Then it takes the B path and it reaches back or circles back to state 1. This is of course a pressure volume curve. So this is the what we call a cyclic system, or rather a cyclic process. Moving forward, we have a flow process. So what is a flow process? A steady flow process is a process in which matter and energy flow in and out of an open system at steady rates. So in this case, we have both exchange of matter as well as energy with the surroundings. So this is basically an open system and the process takes place in an open system. So if you see the diagram, something with the heat content enters the system along with the matter, and then by following some path it crosses the system boundary and goes out of the system. We can add heat or work, separate work to it, or the flow can perform work on its own. So these are the characteristics of a flow process. Moving forward, we have three very important things: reversible, irreversible, and spontaneous process. What is a reversible process? In thermodynamics, a reversible process is a process whose direction can be returned to its original position by including infinitesimal changes to some property of the system via its surroundings. So what happens actually? The thing that a reversible process takes place in infinitesimal space steps. That is, at a certain time, if we observe the process, we will see that no change is occurring. But there are changes that are occurring which we cannot detect. They are continuous infinitesimal changes that takes the process from one state to another. And if we consider going back, we have to follow the same steps and go back to the initial state. And not only should the system come back to the initial state, the surrounding should also come back to its initial state if it's a reversible process. Just like if you plant a seed and a tree grows, if you check it from minute to minute, you will not see any growth. But after a certain time, a tree grows from a sapling. But during the small time, the change is not very obvious. You can only see the change after a significant time passes. So reversible process is kind of like that. Next is an irreversible process. In an irreversible process, finite changes are made. Therefore, the system is not at equilibrium throughout the process. At the same point, an irreversible cycle, the system will be in the same state, but the surroundings are permanently changing after each cycle. So in case of an irreversible process, the surroundings does not come back to the initial state, even though the system can come back to the initial state. So these two are very distinctions between the reversible process and the irreversible process. And then there is a spontaneous process. This will become very important on as we go through the course. A spontaneous process is one that occurs by itself without outside intervention. That means to make a spontaneous process occur, we don't have to do anything. It will occur on its own. Just like water from a waterfall falls from the top to the bottom. We don't have to do anything. If we want to do the reverse thing, we will have to use a pump to pump the water from the bottom to the top. So if we draw a curve, this is a temperature versus entropy curve. What is entropy? We will cover it later. So as you can see, the reversible process is a smooth curve, while the irreversible process is a discontinuous curve. Reversible process occurs in very infinitesimal steps, so it appears a continuous curve, but a reversible process occurs in definite steps. Thus, thus it appears like a discontinuous curve. Moving forward, we have discussed how the process works. Now we can see what parameters changes during the process and we can categorize it as such. So there is this isothermal process. Iso means same and thermal basically means temperature. So when the system undergoes change from one state to another but its temperature remains constant, the system is said to have undergone isothermal process. So if a system goes from point 1 to point 2 but the temperature does not change, we call it a isothermal process. If we plot the PV curve, we will see that it is a for ideal gas it is a rectangular hyperbola and pressure and volume changes accordingly following Charles' law and T remains constant. Then there is isobaric process. An isobaric process is one where throughout the change of the system the pressure of the system stays constant. So unlike earlier where the temperature was constant, here we have a process where the pressure is constant. If we consider the PV curve, we will see that we have a straight line parallel to the volume axis in the PV curve for an isobaric process. Next is an isochoric process. An isochoric process is one where throughout the change of the state of a system, the volume of the system stays constant. So earlier it was pressure constant, now it is a volume constant. And if we see the PV curve, we will see a straight line parallel to the pressure axis for the PV curve. Here the volume is constant. Then there is an adiabatic process. An adiabatic process occurs without transferring heat or mass between a thermodynamic system and its surroundings. So an adiabatic process takes place in an isolated system. We have seen the flow process taking place in an open system. Here the adiabatic process is taking place in an isolated system. All others will take place in a closed system. So we will be covering all three kinds of processes. One is the open system, some in the closed system, and some in an isolated system. Adiabatic process is such a process which takes place in an isolated system. And if we consider the curve, we will see that while comparing to a PV curve of an isothermal, the adiabatic curve is a bit steeper. The adiabatic PV curve is a bit steeper than the isothermal curve. And we will see why it is in the later lectures. Moving forward, there is another process which is a polytropic process. A polytropic process in thermodynamics is a type of reversible process. Remember, all the graphs you have seen till now, they were all continuous. Hence, we should assume that they were reversible processes. So, a polytropic process in thermodynamics is a type of reversible process where the relationship between pressure and volume of a system is described by the equation PV to the power n is equal to constant, where n is constant as is known as the polytropic index. This equation encompasses various thermodynamic processes including isothermal and adiabatic by adjusting the value of n. How so? When n is equal to 1, or so rather n is equal to 0, it represents an isobaric process where the pressure is constant. When n is equal to 1, it represents a isothermal process. When n is equal to gamma, it represents an adiabatic process. We'll discuss about gamma later in the course. And when n is infinity, it represents an isochoric process. So the value of n, if it has the significant or rather the prominent values of 0, 1, gamma and infinity, it will represent respectively isobaric, isothermal, adiabatic and isochoric process. Anything in between them, that will be a entirely different process. We are talking about ideal gas here, remember that. So if we plot PV for an isotopic process, as you can see, for the prominent values, we have n is equal to 0 isobaric, n is equal to 1 isothermal, n is equal to gamma adiabatic, and n is equal to infinity isochoric. And when n is equal to n, any other value from these four entities, different from these four entities, we will have a polytropic process. Moving forward, we have talked about the state functions, and now we need to determine how we can say a function is a state function or not. Let us consider ideal gas, 1 mole of it, and then we can write PV is equal to RT. Now let us consider the gas undergoes change in two ways. What are the two ways? First, an infinitesimal change in volume keeping temperature constant, and then an infinitesimal change in temperature keeping volume constant. So these are the two steps of the process. Again, we can first start with an infinitesimal change in temperature keeping volume constant, and then an infinitesimal change in volume keeping temperature constant. So we are following two paths for a system, or rather change of state of a system. So for case 1, we can write P is equal to RT by V. So after infinitesimal change in volume keeping temperature constant, we arrive at del P del V T constant is equal to minus RT by V square. Following by an infinitesimal change in temperature keeping volume constant, we arrive at del 2P del V del T, which is the second derivative, is equal to minus R by V square. Now let us follow the second one. Case 2, the change in pressure after an infinitesimal change in temperature keeping volume constant is given by del P del TV is equals to R by V. Now the change in pressure after an infinitesimal change in volume keeping temperature constant gives us del 2P del T del V is equal to minus R by V square. So from equation 1 and equation 2, what can we find? We find del 2P del V del T is equals to del 2P del T del V. So we took a system, it followed two different paths. At the end of the path, the change of the state of the system that followed the two paths, we arrive at the same value of the parameter or the function pressure. Since it appears that the change in the value of pressure does not depend on the path, rather on the initial and final states, we can conclude that pressure is a state function. So that's all for today. We'll come back with another lecture next time. Thank you.